Hello, everyone. Today, we're going to talk about Java generics. Finally, makes sense. No more confusion. What are generics? Generics allow classes, interfaces, and methods to work with different data types while maintaining compile time type safety. More simply, generics allow you to write one piece of code that works for many types without losing type checking. I tend to think of them as parameterized types. How are generics used in industry? Generics are not an academic feature. They are one of the foundations of modern Java code bases. You see them everywhere, such as lists, optionals, response entities for REST APIs, JPA repositories for databases, comparators to sort, and streams. Without generics, large enterprise Java applications would be runtime error machines. Before Java 5, collections kind of look like this. I mean, notice here that you're assigning a variable list to a new array list, but we're not specifying what types go into the array list. So we're adding a string and we're adding a number, and that's fine. At compile time, this will compile. However, when we run it, this is what happens. We get a runtime error. What generics does is it relocates that error to compile time so that if you don't insert a correct type, you'll know at compile time. Why do generics exist? Generics give us compile time safety and eliminate unsafe casting. They solve three major problems, including class cast exception, code duplication, and unsafe APIs. Instead of writing three different lists, employee list, customer list, and product list, you write one structure, which is a list, which can take in any reference type. We can also create our own generic classes. Even though we have pre-existing generic classes in Java, we can create our own. Like this one right here. We're creating a box class, which takes in a T. And note that this T is used as a placeholder. You can, you can put in a string, an integer, or even another custom-made data type. And we also use letters like E, K, and V. So T would stand for type, E would stand for element, K and V would stand for key value or any. You can technically use any letter, but these are the accepted conventions. So this is our custom type. We have a setter and getter that takes in this T type. We'll run it. And basically it says when we create our own generics, we create classes to work with different data types. For example, if we create a type box, which takes in the string hello, it sets a value of hello. If we have box 2 of type box, which takes in an integer, it sets a value of 1. So we can use generics to create versatile data types. Not only can we make classes generic, but we can make methods generic as well. So we have this class util, which has a static method called print item, and it has a parameterized return type of type T, and it also takes in a type T as a parameter as well. So you can have a return type and a parameter of T. When we run this, we'll see that the method does execute. Okay, we're going to print some items, and the method executes and prints a string, an integer, and a decimal. Polymorphism with generics. It's subtle but very important. So we already have the list interface, which can take in a string or an integer or any reference type. And we can infer the type from what's put in the list. So we can infer types. So we can infer that this is a string, this is an integer. And both objects are different types, but they share the same behavior. And this is also known as parametric polymorphism. We have different types of type parameters. The same class, which is array list, behaves a little differently depending on the type. Let's talk about bounded type parameters. Sometimes you don't want just any type. You want only certain kinds of objects. For example, if we have a calculator class, like like we do here, or a number box class in this case, we want to work only with numbers. We don't want strings. And this is common in sorting, comparison, frameworks, and repositories. So what we can do is let's run this method. Oh, actually, we're not really running this method, but what this is going to demonstrate is we can restrict the kinds of objects that are taken in as type parameters. So this will only take in numbers. So here we have integer, double, float being taken in. These will compile, but if we try to put in a string, this will not compile. Okay, wait for it. All right, see, it's not compiling, bound mismatch. The type string is not a valid substitute for the bounded parameter. T extends number of the type number box. Okay, now that we've talked about bounded parameters, let's talk about wildcards, which is basically an extension of bounded parameters. And this confuses the hell out of people. So wildcards control how a generic type can be used. We have different types of wildcards. We have an unbounded wildcard, which basically says, okay, we don't care what the list contains because we're only going to read the value. And this wildcard is denoted by a question mark. And we're using the list interface as an example. We have upper bounded wildcards, which uses the producer type of behavior. So difference between producer and consumer. So producer it produces data. It produces data. It spits out data. Consumer, it takes in data. So upper bounded wildcard is basically you have this wildcard extending a number. So any subtype of number can be used as a type parameter. You can safely read it, but you can't add to it. Then we have the lower bounded wildcard, which is the consumer. So you can use any parent type, any type that's parent to the integer type as a type parameter. And you can write safely to this. So here's a demo of wildcard. We have an unbounded wildcard, we have an upper bounded wildcard, and we have a lower bounded wildcard. And what we're going to do is we're going to see these wildcards being used in action. So let's play this and see. So these are our three different types of wildcards. Okay, and here's our main method. So in our main method, we're going to use the superhero class for the unbounded wildcard. We're going to use the double class, the double type for the upper bounded wildcard because this method, sum, can take in a number class and any of its subtypes. And then we're going to use an object for the lower bounded wildcard because this add integers can take a number and any parent type of number. An object is every object's parent type. So let's continue to run this. Okay, we got some outputs. All right. All right. So we printed our three superhero classes. We printed a sum of the three doubles, and we printed the list before and after adding object types. So wildcards, the rule that you need to know, and this is interview important. So we have a PECS acronym. So producer extends, consumer super. So if a structure produces data, it extends. If it consumes data, then you use the super keyword. And this one sentence alone can solve 70% of generics confusion. So just remember the PECS. And you can look at this table here for further explanation. Like I was trying to say before, uh, producer, you're taking objects out. Consumer, you're putting objects back in. So when you take objects out, you're reading data. When you put objects in, you're writing data. So you're reading, you extend, write, you use super. Just remember the PECS acronym. While this matters in real work, you cannot properly use string data streams, collection, comparator, functional interfaces, and optionals without properly understanding generics. And here's a real example from Spring Boot. So you have an interface called JPA repository, and that's one of the interfaces responsible for reading and writing to a database. And you can use generics to infer data types, build SQL, generate queries, and map entities. That's why Java frameworks feel like magic. They are actually generic-driven code generation. So in closing, generics allow Java to write reusable, type-safe code. They move errors from runtime to compile time and power most modern Java frameworks, including collection streams and Spring Data. Thank you very much. I am out. Peace.